If the observable universe were somehow shrunk to the size of the United States, our entire solar system would be smaller than a single grain of dust. And Earth, the world that holds every memory you have, every name you know, every story ever told, would be too small to draw, too small to mark, too small to fit anywhere on the map. That's the part most star charts will never show you. Not because astronomers forgot us, but because there is simply no scale in the universe where Earth can be drawn honestly. And yet, you're here tonight, lying on that invisible world, a world so tiny that the cosmos can't make room for it, but somehow big enough to carry oceans, continents, cities glowing after midnight. And you. So before you drift too far into the evening, let me ask you something simple. How small is Earth, really? Not just compared to the sun or the galaxy, or the parts of the universe you've heard about, but on the true cosmic scale, the one where distances stretch beyond anything the human mind was built to hold. Tonight, we're going to zoom out from your room, past the clouds, past the planets, past the edge of the solar system, and we won't stop until we reach the edge of everything we can possibly see. So let's begin where your universe feels the biggest, right here on Earth. Before we leave Earth behind, it helps to remember just how enormous it feels from the perspective you and I live in every day. Think about the world at human scale. Cities glowing through the night, highways stretching further than your eyes can track, mountain ranges rising like walls on the horizon, and oceans covering more than 70% of the planet. A continuous body of water so vast that entire continents look like islands scattered across it. Earth's circumference is about 40,075 kilometers, or roughly 25,000 miles. That means if you could walk without stopping, no sleep, no wind, no weather, it would still take you more than a year to circle the planet once. And that's assuming you could even find a place to walk across the oceans. Its total surface area is 510 million square kilometers, or about 197 million square miles. The United States, for all its size, occupies less than 2% of that. When we say a country is huge, we're usually talking about a fraction of the surface of one single world. And at human speed, the planet feels endless. Drive for 40 straight hours across America, and you'll still be in America. Fly for 15 hours across the Pacific, and you'll only be moving from one side of Earth's watery skin to the other. Climb a mountain, and the horizon hardly shifts. Stand at a beach, and you could stare at the ocean for a lifetime and never see what lies beyond your line of sight. Everything about our daily experience tells us Earth is massive, overwhelmingly, impressively large. But that impression comes from our own size and our own limits. Our legs can only take us so far. Our eyes can only see so much. Our sense of distance was shaped on a planet where far means a few hundred miles, and very far means crossing a continent. From this scale, Earth holds everything. The forests you've hiked through, the cities you've lived in, the countries you've visited, the oceans you've never crossed, and the thin blanket of air, no thicker in proportion than the paint on a globe, that carries every breath you've ever taken. It's true what Carl Sagan once said. The Earth is a very small stage in a vast cosmic arena. But here, at the beginning of our journey, it doesn't feel small at all. It feels complete. It feels like everything. And that's exactly why this moment matters. Because in just a little while, as we begin to zoom out, the same world that feels impossibly large will start to shrink, and then shrink again, until the word large becomes meaningless. Everything that feels big now will soon feel tiny. Earth is the entire universe we can touch, for now. But even our nearest neighbor reveals a truth we're not used to. Space is mostly empty. From where we stand on Earth, the moon feels close. A familiar light that rises and falls with a comforting rhythm. But the moment you leave the surface and step back just far enough to see them as a pair, something surprising happens. The moon is far, far more distant than your eyes ever suggested. The moon has a diameter of 3,474 kilometers, or about 2,159 miles, roughly 27% the size of Earth. If Earth were the size of a basketball, the moon would be a tennis ball. And if you place them side by side the way diagrams often do, almost neighborly, like two close friends drifting through space together. The actual distance between Earth and the moon is 384 kilometers, or roughly 239,000 miles. Far enough to fit 30 Earths between the two worlds, lined up edge to edge. 30. If you drew Earth and the moon to scale on a sheet of paper, both spheres would be tiny dots, and the rest of the page would be nothing but emptiness. And that emptiness is the point. The Earth-Moon system is mostly space. Silent, dark, airless space that separates our world from the smaller companion that has shaped our history for billions of years. And the moon has shaped far more than you might guess. It stabilizes Earth's axial tilt, keeping our climate relatively steady over geological time. Without it, seasons could swing wildly, making long-term ecosystems far harder to maintain. Its gravitational pull drives the tides, stirring the oceans, influencing global circulation, and supporting the delicate intertidal zones, where life once made the jump from sea to land. Even Earth's rotation, its day-night rhythm, has been slowly shaped by the moon's tug, helping regulate the cycles that life depends on. For something that looks so small in the night sky, the moon has kept Earth balanced, breathing, and habitable. But tonight, we're seeing it differently. We aren't looking at the poetry of moonlight on clouds, or the comfort of a familiar crescent. We're looking at the first real taste of scale. The realization that space is mostly nothing, even right next door. Imagine lifting away from Earth now. Clouds shrink into a thin white layer, the continents settle into their shapes, and the blue curve of the atmosphere becomes a fragile halo around a glowing world. Lift a little higher, and the moon comes into view. Not hovering beside us, but hanging far off in the dark, a pale sphere suspended across a gulf that feels too large to describe. Now imagine zooming out further, until both Earth and the moon fit into a single frame. You'd see two spheres on opposite ends of a vast black canvas, with the space between them stretching wider than either world. That empty stretch, that silence, is the first real step into the true universe. It is here between Earth and the moon that you begin to feel the cold truth. Everything familiar sits inside pockets of space so wide and so empty that our intuition collapses. Neil deGrasse Tyson once said, "The universe is under no obligation to make sense to you." And this is where that idea starts to feel real. If this much empty space exists right next door, you're not ready for what comes next. But if the moon made Earth feel small, the sun will make it vanish. Leave the Earth-Moon system behind, and something dramatic happens almost immediately. The emptiness you just saw, that long stretch of darkness between two worlds, is still nothing compared to what waits ahead. Because the moment the sun enters the frame, Earth doesn't just feel small, it loses its size entirely. The sun's diameter is 1.39 million kilometers, or about 864,000 miles. That's 109 Earths lined up across its face. And in volume, it could hold 1.3 million Earths, a number so large it barely feels like a number at all. It's the first real scale shock of our journey. The transition from "this is big" to "this is absurd." And the sun doesn't just dwarf Earth. It dominates the entire solar system. 99.86% of all the mass in our planetary family is inside this one star. Everything else, from Jupiter to comets to the blue world you call home, makes up the final 0.14%. We orbit this star at a distance of 1 astronomical unit, or about 150 million kilometers, 93 million miles. A distance so great that even light, the fastest thing in the universe, needs about 8 minutes and 20 seconds to reach us. At human speed, the numbers get even more unreal. If you could drive a car at 100 kilometers per hour without stopping, without fuel breaks, without sleep, it would take you more than 170 years to reach the sun. A modern jet, flying day and night, would still need over 19 years. This is the real scale of the solar system. Nothing is close, nothing is quick, nothing is human-sized. Now imagine zooming out a little more. Earth, which felt huge just minutes ago, slows into a faint blue bead, a single pixel on a vast black canvas, one of 8 tiny worlds circling a star that fills almost the entire frame. If you try to look for Earth as we keep pulling back, it eventually disappears entirely, swallowed by glare and distance. Earth has no size here. Only its position matters. Its delicate placement inside the narrow Goldilocks zone, where temperatures allow liquid water to exist and life can flourish. A few million kilometers closer, and Earth becomes a scorched desert like Venus. A few million kilometers farther, and it freezes like Mars. The sun controls far more than heat and light. Its magnetic field, carried outward on the solar wind, forms a vast bubble called the heliosphere, shielding Earth from cosmic radiation. Its storms can disrupt satellites, radio systems, and power grids light years more advanced than any ancient navigator who once used its rise and fall to mark the days. And yet, for all this power, the sun is not unusual. It's not a giant, not a dwarf, not a rare jewel in some cosmic collection. It's a perfectly ordinary G-type main sequence star, just one of an estimated 100 to 400 billion stars in the Milky Way. That's the twist. A star so overwhelmingly massive that it erases Earth is still considered average. At this scale, our world is no longer a sphere. It's a location, a coordinate, a thin orbit drawn around a yellow star in a vast, mostly empty arena of dust, gas, and gravity. Physicist Richard Feynman once wrote, "Nature uses only the longest threads to weave her patterns, so that each small piece of her fabric reveals the organization of the entire tapestry." And the sun is one of those threads, binding together planets, comets, magnetic fields, and the fragile conditions that allow life to exist at all. But tonight, it's also something else. The first place in our journey where Earth truly vanishes. And the farther we go, the more dramatic that disappearance becomes. Because if the sun makes Earth disappear, the solar system will make even the sun feel small. When you pull back from the sun's overwhelming blaze, the first things that come back into view are the small, solid worlds huddled close to it. The rocky planets. They look familiar, comfortable, manageable in size after the immensity of the sun. But even here, Earth is not the rule. It's the exception. Mercury appears first, a scorched ember skimming the solar furnace. On its day side, the ground can bake above 400 degrees Celsius, hot enough to soften metal. On its night side, without air to hold the heat, temperatures plunge near 180 degrees Celsius. There's no gentle twilight there, no stable air, no haven for oceans or weather. Only a world beaten by extremes, cratered and silent. It is a planet in shape only, more like a burnt-out moon with a front-row seat to the sun's brutality. Then Venus rises into the frame. At a glance, it feels like Earth's twin. Nearly the same size, nearly the same mass, nearly the same gravity. But the resemblance ends the moment you touch its atmosphere. A crushing blanket of carbon dioxide presses down with a force 90 times stronger than the air on Earth's surface. Clouds of sulfuric acid swirl overhead. And the temperature? Around 460 degrees, high enough to melt lead, high enough to make even Mercury's daylight seem gentle. Venus is a lesson whispered through time. This is what happens when a world slips too far toward the wrong balance. An Earth-sized planet that took one step down a different road and never came back. Earth sits between these two extremes like a narrow bridge. Not too hot, not too cold. Wrapped in an atmosphere that shelters without smothering. cradled in a zone where water can stay liquid, stable enough for life to try, fail, try again, and eventually flourish. Nothing about Earth's size makes this possible. Only the delicate alignment of distance, chemistry, and chance. And then Mars drifts by, a reminder that even almost right is still wrong. It once had rivers, lakes, maybe even coastlines. But with only about half of Earth's size and a fraction of its gravity, Mars couldn't hold its atmosphere. It lost its magnetic shield. Its oceans dried into dust. Its warmth leaked into space. What remains is a cold desert haunted by the ghost of a world that nearly made it. Between Mars and the giant planets lies a region that movies often portray as a chaotic gauntlet, the asteroid belt. In reality, it is mostly empty. Vast stretches of darkness punctuated by solitary rocks drifting far apart. If you stood on one asteroid, you might not even see the next with your own eyes. And all of them combined, every fragment of stone and metal, still way less than Earth's moon. So the inner solar system tells a quiet truth. Earth is not the center of anything. Not the largest, not the closest, not the oldest. Just one rocky world among many. And yet, the only one we know where oceans run, air moves, and life listens. This region was supposed to feel familiar, but instead, it shows just how rare our comfort is. Among these four rocky siblings, Earth isn't the strongest, or the biggest, or the most resilient. It's simply the one that survived long enough to become home. And out there, beyond Mars and the drifting stones of the asteroid belt, the true giants of the solar system are waiting, ready to make Earth feel smaller than ever. Leaving the rocky inner planets behind, you drift into a region of the solar system where scale stops playing fair. Out here, the worlds grow so large, so overwhelming, that Earth begins to feel like a forgotten marble someone left on a distant shelf. The first thing that rises into view is Jupiter. Not as a chapter heading or diagram, but as a presence. Even from millions of miles away, it fills your vision like a rising storm. Its diameter is 11 times Earth's, and its volume could hold more than 1/300 Earths without breaking a sweat. Every storm you've ever seen on Earth, every hurricane, every cyclone, becomes trivial compared to the Great Red Spot, a churning vortex wider than our entire planet, spinning for centuries in an atmosphere deeper than any ocean we've ever known. And yet, Jupiter is more than a monster of gas and storms. It's the anchor of the solar system, a world so massive it outweighs every other planet combined. Its gravity bends the paths of comets and asteroids, catching some, redirecting others. A silent guardian that has probably saved Earth more times than we'll ever be able to count. Keep drifting outward, and a soft, golden glow begins to appear. Saturn. It's smaller than Jupiter, but still nearly 10 times the width of Earth. From afar, the rings look solid like a cosmic halo. But as you move closer, they dissolve into countless shards of ice and rock, spread across hundreds of thousands of miles, yet thinner than the height of a house. They shimmer like snow caught in sunlight, ancient, delicate, and temporary. One day on cosmic timescales, those rings will fade, leaving Saturn bare once again. Orbiting Saturn is a world that feels eerily familiar. Titan doesn't look like Earth, but it behaves like one. It has a thick atmosphere, thicker than ours, and a full liquid cycle with lakes, rivers, and seas. But instead of water, they're filled with liquid methane and ethane. Under a dim orange sky, waves lap against frozen shores. It's cold enough to harden steel, yet strangely, the patterns of weather and erosion echo the ones carved by water back home. Titan is not a twin of Earth, more like a dream of Earth, drawn in a colder palette. And then there's Enceladus, small enough to fit beneath the state of Arizona, bright enough to look like a polished pearl. Nothing about its surface suggests motion or life. But beneath the crust of ice lies a surprise. towering plumes of water vapor escaping into space through cracks near its south pole. Those plumes tell us there is an ocean beneath the ice, a global ocean, warmed by tidal forces and rich with the chemical ingredients that life, at least microbial life, might require. A world the size of a city, hiding an ocean the size of Earth's seas. It almost feels unfair how casually the universe scatters mysteries. Farther out, Uranus rolls through space like a tipped-over globe, spinning almost on its side with a tilt of 98 degrees. Seasons there last decades. One hemisphere basks in sunlight for 40 years, while the other lies in darkness. Neptune, the last of the giants, crackles with winds that reach 2,000 kilometers per hour. The fastest atmospheric winds in the solar system. Its storms appear and vanish without warning. Dark shapes swirling across a blue world colder and more distant than anything we've passed so far. Through all of this, something important becomes clear. Earth isn't just small. It is unremarkable in size, dwarfed by giants, overshadowed by moons that hold oceans and atmospheres of their own. If life needs water, chemistry, or energy, then maybe the best places to look aren't planets at all, but these strange, unexpected moons. Carl Sagan once wrote, "Somewhere, something incredible is waiting to be known." Out here among these giants and their impossible satellites, you begin to understand exactly what he meant. And yet, for all their size and beauty, this entire family of worlds, every storm, every ring, every ocean hidden beneath ice, is just a tiny island, floating in a much larger sea. But even this grand family of planets and moons is just a tiny island, drifting in a far larger ocean. Once you drift past Neptune, everything starts to feel strangely quiet. The sunlight fades into a pale, cold glow, and the familiar structure of the solar system, those neat, circular diagrams you've seen all your life, begins to unravel. Out here, the planets no longer define the borders. The real solar system stretches much farther, into a frontier made of ice, darkness, and distance. The first region you enter is the Kuiper Belt, a vast ring of frozen debris that circles the sun from about 30 to 50 astronomical units away. This is the realm of Pluto, Eris, Makemake, and countless smaller bodies, relics left over from the solar system's formation. Despite the way textbooks often portray it, the Kuiper Belt isn't a dense field of tumbling boulders. It's mostly emptiness. Each icy world is separated from the next by enormous gulfs of dark space. Even the largest objects, Pluto with its thin atmosphere and bright, heart-shaped plain, are tiny islands drifting in a silent sea. Many of the short-period comets we see from Earth likely begin their journey here. Their stretched, tilted orbits hint at how chaotic and unsettled this region truly is. But even the Kuiper Belt, with all its frozen ruins, is just the inner edge of something far larger. A structure so enormous, we've never seen it directly. Beyond the belt, the darkness deepens into something almost mythic. The Oort cloud, not a ring, but a spherical shell surrounding the solar system like a ghostly bubble. We believe it extends from roughly 50,000 AU to perhaps 100,000 AU, nearly 2 light years from the sun. At that distance, the sun is no longer a blazing star. It's just another pinpoint in the cosmic night. We only know the Oort cloud exists because of the comets that fall toward us from every direction. Long-period travelers whose orbits stretch so far, they must come from a distant reservoir no telescope has yet touched. Jan Oort understood this from the way those comets behaved, the way their ellipses pointed back to a place no spacecraft has ever visited and may not reach for thousands of years. To understand the scale, imagine the solar system out to Neptune shrunk to the size of a compact disk. At that scale, the Oort cloud would be the size of an entire sports stadium surrounding it. The planets, all 8 of them, would sit crammed into a tiny dot at the center, barely noticeable inside a bubble vast enough to swallow every diagram you were ever shown as a child. Earth, with all its continents and oceans, lies buried deep inside that central speck, not at the edge, not even close. The solar system is not a tidy stack of orbits. It is a huge, mostly empty bubble with a few bright grains clustered near the core. And the most astonishing part? The outermost edge of the Oort cloud lies almost halfway to the next star. Our home system, the one we imagine as a small, simple neighborhood, is actually an enormous void, a bubble drifting alone through interstellar space. And beyond that ghostly bubble of ice and rock, the true void begins, the space between the stars. Drifting beyond the Oort cloud, you finally leave the domain of the sun. At this distance, the solar system no longer feels like a system at all. Just a faint bubble of influence fading behind you. Ahead lies something far stranger than planets, rings, or icy debris. The space between the stars. And the first lighthouse in that dark ocean is Proxima Centauri, the closest star to our sun. Close, of course, is only a word our human vocabulary tries to borrow. Proxima sits 424 light-years away, a number simple to say, but nearly impossible to grasp. A light-year isn't time, but distance. The distance light covers in 1 year while racing at 300,000 kilometers per second. In the time it takes you to blink, light has circled Earth 7 times. In a year, it travels 9.46 trillion kilometers. So when we say Proxima is 4.24 light-years away, what we really mean is your fastest thought, your quickest reflex, your entire sense of speed is useless here. Try shrinking the solar system to something familiar. If the distance from the sun to Earth, 1 astronomical unit, were just 1 centimeter, then Proxima Centauri would sit more than 2 kilometers away. 2 kilometers for 1 star, 1 centimeter for an entire Earth-Sun separation. Or imagine the solar system out to the Oort cloud as a single compact disk resting on a table. On that scale, Proxima would be another compact disk, but lying hundreds of meters away, across a field, beyond the edge of what you can see. Proxima itself isn't even impressive by stellar standards. It's a dim, cool red dwarf, far smaller and fainter than the sun, a quiet ember compared to a bright flame. Yet, it represents the nearest possible destination outside our home system. And even that nearest neighbor may as well be another universe, because moving through interstellar space is nothing like traveling between planets. Planets are close. Stars are isolated. Consider Voyager 1, the farthest human-made object from Earth. Launched in 1977, it has been racing into the dark for over 4 decades at about 17 kilometers per second. Fast enough to cross the United States in just a few minutes. It has already passed through the sun's heliosphere, touching the edge of interstellar space. And yet, after all this time, Voyager 1 has traveled only 1/5000th of the distance to Proxima Centauri. If Voyager were headed straight toward Proxima, which it isn't, it would take tens of thousands of years to arrive. Entire civilizations could rise and fall while that small metal craft moved from one star to the next. That's the scale we're entering now, a realm where distance stretches so far that every measure we use in everyday life collapses. Kilometers, miles, even astronomical units. None of them are big enough. Light years are the smallest unit that makes sense anymore. And yet, for all its emptiness, interstellar space is not truly empty. It's a thin mixture of gas, dust, and magnetic fields, far thinner than the best vacuum we can make in a laboratory. A place where a single grain of dust might be separated from the next by the space of a city, where stars are like scattered streetlights, separated by deserts of darkness on every side. This is the real structure of the galaxy. Isolated islands of light, each surrounded by vast oceans of night. And somewhere inside one of those tiny islands is Earth, a world already small inside its own solar system. now reduced to a memory inside a much larger void. Every spacecraft we've ever launched, every signal we've ever sent, every attempt at exploration has barely stepped beyond the front porch. The space between stars is a wall, not a physical one, but a conceptual one. A reminder that even with billions of suns in the Milky Way, crossing from one to another is a journey so long that our species has not yet figured out how to measure it emotionally. Neil deGrasse Tyson once joked, "Space is big, really big. You just won't believe how vastly, hugely, mind-bogglingly big it is." Out here, it doesn't feel like a joke. It feels like reality finally telling the truth, and all of these tiny, distant islands of light. Together, they form something even more humbling. Our home galaxy. Leaving the space between stars behind, you begin to notice something new taking shape in the darkness. A soft river of light stretching across the sky. At first, it looks like a distant glow. Then, as you pull farther out, it becomes clear. This is not a cloud. It's not a band of fog. It's an entire galaxy made of suns. The Milky Way. Our true home in the cosmos. It's a barred spiral galaxy, a sweeping disk of stars and dust, roughly 100,000 to 120,000 light-years wide, and about 1,000 light-years thick at the disk. Inside this shimmering structure live 100 to 400 billion stars, a population so huge that if you tried to count them one per second, you wouldn't finish in a human lifetime, or a million of them. And our sun, the star that feels enormous in every part of human history, is just one small, ordinary dot among them. We've lived our entire existence inside a single spark among hundreds of billions. If you zoom in and place a tiny pin somewhere along one of the Milky Way's spiral arms, not even a full arm, but a small spur between the grand ones named Sagittarius and Perseus, that is where the solar system sits. A minor side street in a galaxy filled with cosmic highways. We call our neighborhood the Orion Spur, and from here, the sun orbits the galactic center from a distance of about 26,000 light-years. It takes roughly 225 to 250 million years to complete one full rotation around the galaxy. A galactic year. To put that in perspective, when the dinosaurs first roamed Earth, our solar system was on the opposite side of the galaxy. Since then, we've made just one full lap. As you drift outward, the Milky Way's structure becomes more defined. The bright, crowded central bulge glows with billions of old stars packed tightly together, orbiting under the immense gravitational influence of something extraordinary. Sagittarius A, a supermassive black hole about 4 million times the mass of the Sun. It doesn't sit there devouring the galaxy. Instead, it acts like an anchor, keeping the stars in the inner region moving along their natural paths. Move away from the bulge, and the spiral arms unfurl like glowing ribbons. These arms host nebulae, stellar nurseries, and clusters of young stars. The Orion Nebula, for example, is a cradle of newborn suns, a place where gas and dust compress under gravity to ignite the next generation of stars. The Pleiades, shimmering in blue light, mark a cluster of hot, young suns wrapped in drifting dust. Farther out, in the galactic halo, scattered ancient stars in globular clusters like M13 orbit silently, surrounding the galaxy in a faint spherical shell. If you could stand on a planet near the Milky Way center, the night sky would never be dark. It would glow like a permanent twilight, filled with so many stars that shadows would disappear. But far in the outskirts, where our solar system lives, the sky is thin, quiet, almost lonely. We see only the nearest lights, unaware of the empire of stars stretching around us. From a great distance, the entire Milky Way becomes a single, elegant form, a glowing pinwheel floating in a black sea. Our sun, Earth, and every human life fade into a location too small to mark. Not even a pixel, not even a dust mote. For the first time in this journey, you understand that Earth is now a speck on a speck inside a disk of light that spans 100,000 light-years. A world that once felt large under your feet has become insignificant in a swirl of billions of suns. And yet, there's a strange comfort in that. A quiet realization that we belong to something vast, ancient, and beautifully organized. Carl Sagan once wrote, "Our galaxy is 100,000 light-years across. A single human life is too tiny a flicker to notice in that sweep." And as you look at the Milky Way from the outside, that truth becomes clear. The galaxy is immense. We are small, and the universe is larger still. But the Milky Way itself is not alone. It is just one leaf in a much larger cosmic forest. When you rise far enough above the Milky Way, something unexpected happens. The galaxy, that impossible pinwheel of stars stretching 100,000 light-years, stops feeling large. It becomes just one glowing leaf drifting in an enormous forest. And the first trees of that forest are the galaxies of the local group. From above, the Milky Way and Andromeda look like two great lanterns suspended in darkness, separated by 2.5 million light-years. That distance, close by cosmic standards, is still so vast that even a beam of light, the fastest thing we know, needs 2.5 million years to cross it. Andromeda is slightly larger than us, home to perhaps 1 trillion stars, and locked with the Milky Way in a slow, inevitable dance. In about 4 billion years, the two galaxies will merge, reshaping both into something entirely new. Around these giants drift dozens of smaller galaxies, dwarf spheroidals, irregular shapes, faint smudges barely bright enough to detect. In total, the local group contains around 50 to 60 galaxies, a small family, moving together through space. But families have neighbors. And beyond ours lies something far bigger. Rising even higher, the darkness brightens again, not with stars, but with whole clusters of galaxies. You begin to see the Virgo cluster, a shimmering metropolis containing thousands of galaxies, each one as grand as or grander than the Milky Way. The cluster sits about 53 million light-years away, and its gravitational influence helps govern the motion of nearby galaxies. At this scale, the Milky Way and Andromeda are no longer dominant players. They're outlying suburbs, one quiet district in a much larger superstructure. And that superstructure has a name: Laniākea. The word comes from Hawaiian, meaning immeasurable heavens. It's a fitting name. Laniākea spans about 520 million light-years and contains roughly 100,000 galaxies, all moving together like water droplets drifting down the same vast slope of space-time. The Milky Way is just one of those droplets, sliding slowly toward a point astronomers call the Great Attractor. We can't see the Great Attractor directly. It lies behind a dense band of Milky Way dust called the Zone of Avoidance. But we know something massive sits there. Its gravity pulls entire clusters toward it at hundreds of kilometers per second. And beyond even that region lies the Shapley supercluster, one of the most massive concentrations of galaxies in the nearby universe, tugging on Laniākea from afar. At this level, you start to understand that the universe isn't organized like a scattered field of galaxies. It's a tapestry, a structure with form and pattern. And now comes the most astonishing shift of all. The cosmic web begins to appear. From far enough away, the universe looks like an enormous three-dimensional lattice. Galaxies and clusters align along glowing tendrils called filaments, stretching for hundreds of millions of light-years. These filaments weave together into walls, such as the Sloan Great Wall or the Hercules Corona Borealis Great Wall. Structures so large that human language genuinely struggles to describe them. Between the filaments lie the voids, regions so empty they contain almost nothing at all. Vast, dark caverns of space, millions of light-years wide. The entire cosmos resembles a neural network, as though the universe itself were thinking or dreaming on a scale we can barely comprehend. From a God's eye view, the Milky Way is now gone. Not faded, gone. It no longer appears even as a dot. nor does Earth or the solar system or human history. Every reference point you ever knew has dissolved into the web. Earth, solar system, Milky Way, local group, Laniākea, cosmic web. You are now looking at the largest structure the human species has ever detected. The architecture of the universe itself. A structure so vast that even light struggles to cross it, so ancient that galaxies move through it like dust carried by ocean currents. Brian Cox once said, "We are part of a structure so large that human language breaks when we try to describe it." Looking at the cosmic web, you finally understand what he meant. And even here, with this enormous network stretched across the darkness like a glowing skeleton, all of it exists inside something even larger. By now you have traveled farther than any spacecraft, farther than any starship in fiction, farther even than imagination comfortably stretches. But there is still one final step outward, one last zoom before the universe reaches its limit. And that limit is not the edge of space, but the edge of what we can see. This is the observable universe, a sphere centered on Earth, roughly 93 billion light-years in diameter. Not because the universe is 93 billion years old, it isn't, but because space has expanded during the 13.8 billion years that light has been traveling toward us. Every photon arriving today has been stretched by cosmic expansion, carrying with it the history of the cosmos. Why is there a boundary at all? Because light travels at a finite speed, and the universe has a finite age. Anything farther than about 5 billion light-years away in any direction simply hasn't had time for its light to reach us yet. The universe might continue forever, but our view of it does not. Inside this glowing sphere lies everything we can measure, everything we can photograph, everything physics can currently grasp. An estimated 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Add them up and you reach a number so large it feels like a typo. 200 sextillion stars, roughly a 2 followed by 23 zeros. More stars than all the grains of sand on all the beaches of Earth. As you pull back, galaxy clusters merge into superclusters, which merge into colossal filaments, strands of light stretching across hundreds of millions of light-years. These filaments weave together into walls, forming the scaffolding of the cosmic web. And between them lie the voids, regions of space so empty that they are nearly indistinguishable from nothing. Everything you've seen on this journey, the sun, the planets, the Milky Way, Laniākea, fits comfortably inside this single sphere. The observable universe is the largest structure we can access, the boundary of human cosmology. But here's the twist. The observable universe is not the universe. It is only the part we can see from our position in space-time. Imagine standing in a small bubble of light, surrounded by a darkness that is not empty, but simply unreachable for now. Beyond the bubble, more galaxies almost certainly exist. An unobservable cosmos stretching into distances we may never touch. The universe could be far larger than the part visible to us. It could be infinite. Or it might curve back on itself. Or it may stretch through dimensions we cannot yet perceive. Which brings us gently to a delicate idea. One that science considers seriously, but cautiously. The multiverse. Not as a dramatic Hollywood landscape filled with alternate versions of ourselves, but as a set of possibilities arising from our best physical theories. One idea comes from cosmic inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang. If inflation happened unevenly, different regions of space-time may have expanded into separate bubbles, each with its own physical laws. Our universe would be just one bubble among countless others. Another idea appears in quantum mechanics, where the many worlds interpretation suggests that every quantum event produces multiple outcomes, parallel realities branching endlessly. In this view, every measurement is a fork in the road. string theory offers another perspective. A vast landscape of possible universes, each with different values for the fundamental constants. Gravity, electromagnetism, the masses of particles. But here's the honest truth, spoken clearly. There is no direct evidence for other universes. Not yet. The multiverse is not a fact. It is a mathematical possibility, an attempt to explain puzzles that remain open. Max Tegmark once said, "Our universe might be just one island in a vast cosmic archipelago. Perhaps. Or perhaps our one island is all there is." Tonight, the point is not to prove the multiverse or dismiss it, but to acknowledge how much larger reality might be than the part our telescopes can capture. As you look at the observable universe from this vantage point, the scale becomes almost overwhelming. The entire cosmos, everything we know, appears as one glowing bubble suspended in something even larger. And inside that bubble, Earth is not just small, it is non-existent. Its location cannot be identified. Its presence cannot be marked. Every memory, every civilization, every thought fits into a region so tiny that it disappears from this view entirely. This is the summit of the journey, the highest point we can reach with modern science, the farthest zoom out available to human understanding. And now that you've seen the biggest picture, the only direction left is back. So let's turn around and begin the long journey home. As you drift at the edge of the observable universe and begin the long journey home, something subtle shifts. The scale of everything starts to contract. Galaxies become clusters, clusters become stars, and soon, individual suns come into focus again. But before we return to our own, there is one truth we need to face. Earth is not unique, not in size, not in type, not even in location. The first clue comes from the planets we found orbiting other stars, worlds we call exoplanets. 30 years ago, not a single one had been confirmed. Today we've identified more than 5,000, and every year that number climbs. With each discovery, the universe becomes less human-centered and more diverse than we ever imagined. Some of these worlds are nothing like Earth. There are hot Jupiters, gas giants so close to their stars that a year lasts only a few days, their atmospheres boiling in the stellar heat. There are mini Neptunes, small icy worlds wrapped in thick envelopes of hydrogen and helium. There are super-Earths, rocky planets bigger and heavier than ours, some with surfaces that might hold oceans, continents, and weather patterns beyond our current imagination. But the most important category, the one that reshapes our place in the cosmos, is the most ordinary one. Small, rocky planets like Earth. NASA's Kepler mission revealed a profound discovery. Planets like ours are common, very common. Studies suggest that 20 to 50% of Sun-like stars could host an Earth-sized planet in the habitable zone, where temperatures might allow liquid water. In the Milky Way alone, that translates to billions of potential Earths. Not metaphorically, literally. And when you consider the 2 trillion galaxies in the observable universe, each with hundreds of billions of stars, you begin to understand that Earth is not the rare jewel we once believed. It is one member of a vast cosmic population of rocky worlds, orbiting ordinary stars in ordinary places. Zooming back from the cosmic web to the Milky Way, Earth becomes even more familiar. Our planet orbits a G-type star, a perfectly average yellow sun. It sits in the Goldilocks zone, yes, but so do countless others we've now observed. It's not the largest rocky world, not the smallest, not the warmest, not the coldest. In almost every measurable way, Earth is a typical representative of a very common class of planet. And that is the twist. For centuries, humanity looked up at the sky and assumed Earth was special, carved out with unique purpose. But what modern astronomy shows is almost the opposite. Nature seems to produce Earth-sized, Earth-like planets with surprising efficiency. Our world is not a cosmic exception. It's a cosmic expectation, which leads to a new way of seeing home. The extraordinary thing about Earth is not its size, or its orbit, or its geology. The extraordinary thing is life. Whatever spark turned chemistry into biology, whatever process transformed simple molecules into something that could reproduce, evolve, and eventually wonder about the universe. That might be the rare part. Sarah Seeger put it simply: for the first time in history, we have the technology to find out if we are alone. And that sentence carries the weight of everything you've seen so far. As we continue our journey back, Earth becomes physically larger again, but conceptually smaller. It is not a privileged world, not a cosmic outlier. It is one example among billions, a reminder that if life exists elsewhere, it has had countless opportunities to appear. And if life has had countless opportunities, there is one question we must ask before going home. If Earth isn't rare, where is everyone else? As you continue falling back in from the vastness of the cosmic web, the universe begins to resolve again into individual stars. But instead of seeing familiar suns, the landscape becomes stranger, more extreme, more difficult to process with human intuition. This is the realm where the word big loses meaning, and small becomes just as deceptive. The first stars you pass are the quiet ones, red dwarfs. They are the most common stars in the universe, far more numerous than suns like ours. They burn slowly, gently, using their fuel with such restraint that they can shine for tens to hundreds of billions of years, far longer than the universe has existed so far. Many of them host planets, some rocky, some close enough for warmth, some perhaps stable enough for life to emerge and evolve at a pace the universe itself hasn't had time to show us yet. A red dwarf is dim, small, and easy to overlook, but it might outlive everything else we know. Move a little farther, and you encounter stars like our own, G-type suns. Our sun feels enormous from Earth, but in the context of the galaxy, it is simply ordinary. Not too hot, not too cold, not too massive, not too faint. Stars like this live for a few billion years, long enough for complex chemistry to evolve into biology, long enough for organisms to learn to walk, think, build telescopes, and wonder where they came from. But keep going, and the universe stops being reasonable. Suddenly, the dark is pierced by a star so huge it borders on the absurd. A red supergiant like Betelgeuse. Its swollen atmosphere could swallow Earth's entire orbit. Some hypergiants, like UY Scuti or VY Canis Majoris, are so large that if they replaced our sun, even Mars would orbit inside their outer layers. Stand at a safe distance from such a star, and it would dominate the entire sky. A cosmic furnace so vast it makes planets look like dust. Yet size alone is not where the universe becomes extreme. Because the moment stars die, they rewrite the rules. The remnants they leave behind break intuition in ways nothing else does. A white dwarf, for example, is roughly the size of Earth, but it packs in the mass of the sun. A single spoonful of its matter would weigh tons. It glows faintly with leftover heat, like a piece of iron cooling after being removed from the forge, slowly fading for billions of years. Then there are neutron stars, even more impossible. Only about 20 kilometers wide, yet heavier than the sun. A teaspoon of neutron star matter would outweigh a mountain. Some of them spin dozens or even hundreds of times per second, sweeping lighthouse-like beams across space. We call those pulsars. Their density is so unimaginable that the atoms themselves collapse, their electrons and protons pressed into pure neutron matter. A city-sized object with the mass of a star. Push beyond even that, and you find the strangest remnant of all, the black hole. Not an object in the traditional sense, but a region where gravity becomes so extreme that space and time themselves are pulled inward. Light cannot escape, Information appears to fall out of the universe. Some black holes are formed from dying stars, but the ones at galactic centers, like the 4 million solar mass monster in the Milky Way, are far larger, shaping the movement of stars across entire regions of the galaxy. In this landscape of extremes, where stars can be smaller than cities or larger than planetary orbits, Earth settles into a strange middle ground, bigger than asteroids, comets, and many moons, tiny next to giants or collapsed remnants. A world that is neither extreme nor exceptional, not too dense, not too massive, not too bright. A planet that exists almost exactly in the middle of nature's enormous spectrum. And that is the quiet truth this segment reveals. Big and small are meaningless here. Earth is not tiny or huge. It's simply one example along a continuum so wide that human language collapses at both ends, which sets the stage for a very different question. One that has nothing to do with size at all. Subrahmanyan Chandrasekhar once said, "In the stellar furnace, gravity and light wrestle for billions of years, and in that struggle, the universe writes its grandest stories. But the story we care about most isn't written by stars. It's written by something far more fragile. And to truly understand how small Earth is, we have to go the other way, not out, but in. As the cosmic view collapses inward, galaxies fade, stars dissolve, and the solar system returns to its familiar proportions. You keep going. Past Earth, past landscapes, past the level where continents and oceans even matter. The journey turns inward now, toward a universe hidden inside every grain of sand, every breath of air, every cell of your body. You are made of atoms, roughly 1028 of them. Enough that if you counted one every second, you'd still be counting long after the last star in the Milky Way burned out. And yet, each atom, despite its unimaginable number, is mostly emptiness. Imagine an atom scaled up to the size of a stadium. At its center sits the nucleus, a cluster of protons and neutrons. But it's not a boulder or a sphere you can picture. At stadium scale, the nucleus would be the size of a pea, resting quietly in the middle of the field. The electrons, which give atoms their size, their chemistry, their structure, wouldn't be orbiting like planets. They'd be like faint specks of dust swirling around the outer seats, appearing and disappearing in a haze of probability. Everything between that tiny nucleus and the ghostly electron cloud is empty space. If matter were compressed down so that all empty space was removed, the entire human race could fit into a sugar cube. And yet this emptiness is what gives matter its shape. The chair you sit on, the air you breathe, the bones in your arms. All of it is built from these mostly empty structures. Millions of trillions of them cooperating in silent, perfect patterns. Go deeper still. The nucleus of that atom, already so small it strains imagination, is not fundamental. Protons and neutrons are made of even smaller components, quarks bound together by gluons in a shimmering fog of quantum fields. At this level, the idea of position becomes blurry. Things don't exist in neat, fixed locations. They exist in clouds of probability. The deeper you look, the more the universe begins to feel less like a machine and more like a set of mathematical whispers. Now zoom back out slightly and ask a simple question. What exactly is Earth made of? The answer is a number we almost never think about. The planet contains on the order of 1050 atoms. 100 trillion 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 trillion. Every mountain, every wave, every drop of rain is built from these tiny systems, each one a miniature solar system of empty space, held together by forces that are both delicate and impossibly strong. The Earth, that felt so small against the Milky Way, becomes unfathomably vast when viewed from the inside. A sphere of atoms arranged into oceans, crusts, gases, and living beings, all of them constructed from mostly empty space. You are a collection of vibrating probabilities. The planet is a collection of collections, And even the densest rock is a cathedral of emptiness. Which brings the journey into a strange symmetry. The universe above you is enormous and mostly empty, and the universe within you is tiny and mostly empty too. At both extremes, the cosmic and the atomic, the pattern repeats. Space dominates. Matter is the exception. Everything we touch, everything we know, is built from the slightest sprinkling of substance inside oceans of nothingness. Feynman once said, "There's plenty of room at the bottom." And standing here, halfway between galaxies and quarks, you finally understand what he meant. There isn't just room, there's an entire world down there. So the scale question twists one more time. Earth isn't simply small or large. It is both. Vast when seen from within, invisible when seen from without. A universe embedded inside another universe. And that duality leads naturally to the next mystery, perhaps the biggest one of all. So in a universe that is enormous above us and almost empty within us, why does anything as fragile as life exist at all? As the microscopic universe folds back into the macroscopic one, and Earth begins to take shape again in your mind, a new question rises naturally from everything you've seen so far. A question as old as wonder and as sharp as science. If the galaxy is overflowing with stars, and if planets like Earth are common, where is everyone? This is the heart of the Fermi paradox. The contradiction between the high probability of extraterrestrial civilizations and the complete silence we observe. Look at the Milky Way alone. Hundreds of billions of stars. Look at what Kepler taught us. Perhaps billions of Earth-sized planets orbiting in habitable zones, if even a tiny fraction of those worlds developed life. And if even a tiny fraction of those forms of life developed intelligence, then the night sky should be full of evidence. Radio signals, megastructures, engineered planets, something. But it isn't. We've been listening for decades. The silence is still absolute. There are several ways scientists explain this silence, none of them speculative in a Hollywood sense, just sober, physical possibilities. Perhaps life itself is rare. The leap from chemistry to biology may be so improbable that it happened only once in an entire galaxy. Maybe the early Earth was struck by a perfect sequence of accidents. The right atmosphere, the right oceans, the right molecules, all at the right moment. Or perhaps life is common, but intelligent life is rare. Microbial ecosystems might flourish everywhere, but turning simple cells into complex organisms, then into tool users, then into technological civilizations, might require a chain of luck almost impossible to repeat. Another possibility is that civilizations don't last long. They may bloom quickly, invent technologies, reach for the stars, and then fade. War, environmental collapse, asteroid impacts, gamma-ray bursts, or simply the quiet entropy of a species that exhausts its resources before escaping its home world. The universe may be full of civilizations, but each one burns out before it can send a greeting across the void. Or maybe civilizations are out there, but too far, too faint or too quiet. The distances between stars are so immense that even radio waves take years, centuries, millennia to travel between systems. A signal we sent today to a promising Earth-like planet might not reach them until long after our society has changed beyond recognition, and their reply might arrive long after ours is gone. Some scientists suggest something hauntingly simple. We may be early. The universe is only 13.8 billion years old. Stars like the Sun will live for billions more. Life may eventually become common, just not yet. Humanity may be among the first sparks in a universe still gathering the conditions for complexity. But to understand this paradox fully, we have to look inward, to the origin of life on Earth. All known life shares a common ancestry. Whether you're a human, a tree, or a bacterium, your lineage threads back to a single ancient cell. That cell was built from carbon, water, and chains of molecules that could copy themselves, DNA or RNA, or a precursor of both. We understand evolution quite well. What we don't understand is how the first spark lit. Did life begin in a primordial soup, brewed by sunlight and lightning? Did it form in hydrothermal vents deep under the ocean, where minerals and heat created the first self-replicating molecules? Or did the building blocks arrive on comets and asteroids, cosmic seeds scattered across young worlds? We don't know. Not yet. And that uncertainty reveals something humbling. In this entire cosmic journey, from quarks to atoms to galaxies, the only place we've seen life for certain is here, on this small world, around this ordinary star. It may be that the universe is teeming with life, but the distances between living islands are too great for us to hear each other's whispers. Or it may be that, for now, Earth is an anomaly, a fragile bubble of chemistry that learned to think, to feel, to ask questions no other world has asked yet. Enrico Fermi once asked simply, "Where is everybody?" And Carl Sagan offered the quiet counterweight, "We are a way for the cosmos to know itself." That may be the strangest truth of all. In a universe saturated with emptiness, silence, and cold, Earth might be one of the very few places where matter has arranged itself into something capable of noticing its own existence. The special thing isn't Earth's size, it isn't its orbit, it isn't its geology. The special thing is you, a fleeting spark of awareness on a dust-sized world. And that brings us back, full circle, to the question we started with. How small is Earth, really? And what do we do with that knowledge tonight? You've traveled so far tonight, farther than any spacecraft, farther than any photon your eyes will ever catch, from the quiet room you're lying in, to the whole Earth beneath your feet, past the moon, the sun, the giants of our solar system, through the Kuiper Belt and the ghostly Oort cloud, out into the dark sea between the stars, across the spinning arms of the Milky Way, into the drifting rivers of Laniākea and the glowing threads of the cosmic web itself. And then, as if that weren't enough, you stepped outside the bubble of the observable universe and gently turned back. On your way home, you saw other Earth-sized worlds, other suns, other possibilities. You passed the enormous and the impossible. Supergiants swollen beyond imagination, neutron stars packed tighter than thought, and atoms. Tiny universes made mostly of nothing. And somewhere in that long descent from the infinite to the infinitesimal, Earth appeared again, small, blue, quiet, and waiting. So now, let's answer the question you came here with. How small is Earth, really? On the map of the universe, Earth is effectively zero. A speck in a system that's a speck in a galaxy that's a speck in a structure so enormous that numbers fail and language folds. It is a dust mote floating in a vast ocean with no shore, one island among 2 trillion galaxies, each galaxy filled with hundreds of billions of stars and more planets than you could count in a lifetime of counting. And our world? It circles an ordinary star, far from the center of its galaxy, far from anything that might be called important. Nothing about its position marks it as special, but small is not meaningless. Because Earth is the only place, so far, where the universe has learned to ask questions, where matter has arranged itself into something that can feel curiosity and fear and comfort and wonder. Out of all the cold and empty dark, this is the one place we know where life breathes, where minds think, where someone like you can lie down at the end of the day and reflect on everything. The universe may not know your name. It may not care whether you answer your emails tomorrow or the day after. But you are part of the tiny fraction of it that can feel awe when looking at the night sky. And that alone is immense. All the things that wait on you today, the deadlines, the small arguments, the unfinished tasks, shrink to the scale they truly occupy. Smaller than a grain of sand in a world made of atoms that are mostly empty space. Small, not in a dismissive way, but in a freeing way. You don't have to carry the universe tonight. It runs on its own. The galaxies will drift, whether you worry or not. The stars will shine without your supervision. The cosmic web will stretch and flow exactly as it has for billions of years. You are allowed to rest. Let the universe be vast. Let it be ancient. Let it be silent and indifferent and beautiful. It doesn't need you to stay awake to keep it running. You are small enough to let go. Small enough to breathe, to soften, to sleep. And that might be the quiet blessing of your place in the cosmos. You live on a world tiny enough, peaceful enough, sheltered enough that you can drift off while thinking about galaxies. In all this immensity, that you exist at all is remarkable. That you get to feel tired is a privilege. That you get to rest is a gift. So close your eyes. Let your thoughts settle like dust in a sunbeam. Let the world beneath you spin gently in the dark. You don't need to do anything more tonight. You've already traveled farther than any map could measure. So let the galaxies spin without you for a while. Let the universe be vast and silent. Tonight, on your very small world, you are allowed to sleep.